Hi students, today we are going to be discussing how we can use Avogadro's number as a conversion factor. Remember, the last time we spoke, we were using molar mass or grams per moles from the periodic table as a conversion factor. Well, today's conversion factor is different. Avogadro's number, which is 6.022 times 10 to the 23rd molecules per mole, is the same no matter what compound you're dealing with. So if I'm talking about donuts and I want a mole of donuts, I need 6.022 times 10 to the 23rd. If I'm talking about apples and I want a mole of apples, I need 6.022 times 10 to the 23rd. And if I'm talking about water molecules and I want a mole of water, I also need 6.022 times 10 to the 23rd. And so that's really what our focus is going to be today, is how we can use Avogadro's number as a conversion factor. The benefit is you don't have to solve for molar mass. It's always the same value. The drawback is that entering numbers like 6.022 times 10 to the 23rd into your calculator leaves more room for error. So in this section, I implore you, I'm begging you to please get out the calculator that you will use for the test and learn how to do these mathematical operations on your calculator. So as I mentioned, for these conversions from moles to molecules and molecules back to moles, we will be using Avogadro's number, or it's sometimes referenced as N sub A, so big N, little a, the number of Avogadro. You will know that you need Avogadro's number because in the question, it's going to say how many molecules or how many atoms are in. Or if you have this many molecules or atoms, how many moles or how many grams. So this question is going to have molecules or atoms as one of the units, either the given or what you're trying to find. So if you need to use Avogadro's number, you're going to see either molecules or atoms in the question. So the first question we want to answer is, how many molecules are in 1.5 moles of water? So now it's time to get out that piece of paper and maybe your periodic table, definitely a calculator, definitely a pen, and we'll go over this one together. As I'm sure you remember, whenever we are doing a conversion problem, we need to start with what we're given as a fraction over 1. Now in this case, I am given 1.50 moles of water, and so again, I put my 1.50 and both units, MOL and H2O, on my fraction. So I am looking to convert to molecules of water. So in my second fraction, I'm going to get rid of moles of water. Remember, whatever's on the top of one fraction cancels down to the bottom of the next. And because I'm looking for molecules, I'm going to put molecules of water on top. Molecules is abbreviated. Its biggest abbreviation is MOLEC. That's it. You have to write out at least that much. Molecules of water, MOLEC. So once I have found that I'm looking for molecules and those are on the top of my fraction, now I can plug in my conversion factor. My conversion factor, whenever I have moles and molecules, my conversion factor is going to be Avogadro's number, or N sub A, which is 6.022 times 10 to the 23rd molecules per mole. And just like when we were talking about grams per mole, molecules per mole is telling me that I have 6.022 times 10 to the 23rd molecules in every 1 mole. So to plug that in up here, I need to actually give myself a little more space. So I have my 6.022 times 10 to the 23rd molecules, and then remember, per mole is telling me that value is a 1. So all I need to do to solve this problem is to multiply through. Multiplying with this kind of a term is pretty easy. What I'm going to put into my calculator here is I'm going to start with 1.50, enter, and then I'm going to be multiplying by 6.022, and don't forget that EXP or times 10 button to the 23rd, and I get 9.03 times 10 to the 23rd. I'm going to round that off to 2 decimal places, so I keep 9.03 times 10 to the 23rd. And the units here, because the moles have canceled, what I'm left with is molecules of H2O. And there we have it, our first problem using Avogadro's number to convert moles to molecules or molecules to moles. Okay, so now we're going to try another one, and we're going to go back in the other direction. So why don't you guys look at this problem right here. How many moles are in 2.107 times 10 to the 24 molecules of salt? And let's get that one started. So for this problem, we're starting with 2.107 times 10 to the 24 molecules of NaCl. An important note here is that it doesn't really matter what this is of. So if it had said salt, but you were unsure of the formula of salt, you can still solve this problem without knowing that the formula for salt is NaCl. Okay, so let's go ahead and cancel. Molecules of salt on the bottom, moles of salt on top. Whenever I have moles and molecules or molecules and moles, I know that I need Avogadro's number. 6.022 times 10 to the 23rd molecules per mole. So the question is, where does the 6.022 times 10 to the 23rd go? And the correct answer is with the molecules. It goes with the molecules. We don't like to say on the bottom or on the top because that sounds like it is a consistent thing. Remember, whether 6.022 times 10 to the 23rd is the numerator or denominator depends on the question. But always, always, always 6.022 times 10 to the 23rd goes with the unit molecules. This is my 1 here. And so now, when I plug this operation into my calculator, I need to divide. So this is going to start with 2.107 times 10 to the 24th. I always recommend hitting, enter because something could go wrong. Let's try that again. 2.107 times 10 to the 24th. There we go. Now it's working right. And this time I need to divided by Avogadro's number, 6.022 times 10 to the 23rd, and I get 3.498, which rounds up to 3.50 moles of NaCl. 3.50 moles of NaCl. Once again, my molecules had canceled, and that's how I know that my last unit here is going to be moles. I want to include the NaCl. I'm properly rounded. One thing you can check, which you maybe know already from math, is that when you're dividing by exponents, you actually subtract the exponents. So if you wanted to estimate what this would be, if you did 2 divided by 6, you're expecting like 0.33 or a third. And then if you do 24 minus 23, you're expecting times 10 the first power. So if you got 0.33 times 10 to the first power, that would be something like 3.3. And we got 3.5, so I feel like my estimation is pretty strong there, and I feel really confident about my answer. It's just a good idea because sometimes calculators do give us trouble to just keep in mind that when we're doing this, we're also doing 24 minus 23. I'm going to circle those guys for you. 24 minus 23. And so I should be getting a number that is less than 10. That's what I'm expecting. So just kind of keeping that in mind as you're going, it helps if you can estimate your math a little bit. So now what we're going to do is you're going to work these 2 problems on your own. So what I'd like you to do is copy these problems down into your notes and then write out the solution for them as best you can. We will go over these answers in class the next time I see you, but these problems are ones you should work out on your own. I will quickly verify the answers as you continue through the video. Notice that I can leave it as sugar because I don't need molar mass, so the identity of sugar really doesn't play a role in the solution to the problem. Also, keep in mind that when you're multiplying, you're adding the exponents, so this is times 10 to the negative 2 plus 23. I'm expecting something in the 21 or 22 range, so this seems like a just fine answer to me. What the calculator gave me was not in scientific notation, so I changed it to scientific notation myself. You should be able to do that on your own. Also, if you put your calculator in scientific notation, it should do it for you. The better answer here is 5.00 times 10 to the negative 1 moles of O2. So far, we have used molar mass and Avogadro's number and the concept of the mole to do two different kinds of conversions. We have learned how to convert between moles and grams using molar mass, and we've also learned how to convert between moles and molecules using Avogadro's number. There is one more conversion factor that we're going to add before we start converting longer distances or over more units at one time. The last conversion factor we're going to learn for this chapter is called the Standard Molar Volume. It turns out that the molecules of a gas at the same temperature occupy the same amount of space regardless of the mass of the gas itself. What this means is that small gases move faster than large gases at the same temperature. So if you imagine the amount of space they cover over time or the amount of area that they require, small gases and large gases, turns out, take up the same amount of space. This is a concept from chapter 14. And of course, we will get there in the future. But for now, what we need to understand is that a single mole of gas occupies the same amount of space, the same volume, regardless of the type of gas that it is. The only thing that matters is the temperature that they are at. So there is a thing called a standard temperature. And the standard temperature is 0 degrees Celsius. At standard temperature, every gas occupies exactly 22.4 liters. And so this leads us to a new conversion factor. The new conversion factor says that the volume of any gas at STP is 22.4 liters for every mole. So every mole of any gas takes up exactly 22.4 liters. And so now we can use this idea to convert from moles of gas to how much space or the volume that that gas might require. 1 mole of any gas occupies 22.4 liters of space at STP. And at STP is an important notation. This is telling us that we are at standard temperature and pressure. STP stands for standard temperature and pressure. So their masses may be different of the gases, but their volume stays the same. This is a graphic showing us that 1 mole of oxygen weighs 32 grams, but 1 mole of oxygen gas takes up 22.4 liters. 1 mole of hydrogen gas also takes up 22.4 liters, but weighs only 2.02 grams. So in this way, we can see that the volume is determined by the number of moles of gas, not the weight or the mass of the gas. So now I know what you're thinking. We can use this conversion factor to convert between moles and liters. So in this section, we will be using standard molar volume in order to convert from moles to volume. This section is really nice because of the standard molar volume being the same for every compound, but also being a nice simple number to enter into your calculator. That makes this particular type of problem the easiest type to do. So if you've been struggling up until this point, please stay with us. Try this kind, because this particular example may be the example that kind of unlocks this mathematical principle for you. So hold on for 2 more problems as we do them together. So first we start with 86.3 moles of O2. And of course, that will be as a fraction over 1. My moles of O2 is going to cancel to the bottom because we're ready to get rid of that. And we are looking for volume, so liters is going to go on top. You keep in mind that the unit of volume is liters, and so that's what we need to use in our conversion. Whenever we see liters and moles together in a fraction, we know that we need standard molar volume, or 22.4 liters per mole. Remember, we read that 22.4 liters per mole. So we're going to go in and plug them in with their units. So 22.4 goes on top and moles gets a 1. So we plug that into our calculator, and as mentioned, this is the easiest kind of plug-in here. All we need to do is 86.3 times 22.4, and we're going to end up with 1933.12 liters of oxygen. But what's even better is to have this in scientific notation. So to put it in scientific notation, it becomes 1.93 times 10 to the third liters of O2. Best answer is the one that's in scientific notation. So the reason why this one ends up being easier is, again, because 22.4 is standard for all compounds, but also it's quite simple to enter into our calculator. We don't have the times 10 to the 23rd issue that we have with Avogadro's number. So let's try one more, last one together. How many moles of ammonia are present in a balloon with a volume of 4 liters? So what you see here is I have used the chemical formula for ammonia, NH3. And you might be thinking, well, I didn't know that. How was I supposed to know that? Well, it's not that you need to know it. As a matter of fact, you don't need to know that to solve this problem. I could just as easily solve the problem by writing it like that. It's just that I don't feel like writing out ammonia. So I'm just telling you here that the chemical formula for ammonia is NH3, and you can feel free to use that to solve this problem. Once we've canceled our liters and put moles on the top of the fraction, we find that we're with moles and liters again, so we're going to use 22.4 liters per mole. Remember, that's 22.4 liters per mole. So 22.4 goes down here and 1 mole on top. That makes this a division problem. 4 divided by 22.4 gives me 0.1785 or 0.18 moles of ammonia. Better would be to put this in scientific notation, in which case I would get 1.79 times 10 to the negative 1 moles of ammonia. So now we've learned all 3 kinds of independent conversion factors and 3 different types of conversions that we can do involving moles. Now what we're going to do is we're going to start putting those concepts together so that instead of just going from grams to moles or moles to liters, we can go from grams to liters. But in order to do that, we're going to need to make a mole diagram. So when next we meet, we will be putting together a mole diagram and then using it to solve more complex converting problems. You guys are doing a great job, and you're almost there to the end of the chapter.